Hello guys and welcome back to PlanckTime. On today's episode we're going to be talking about Kepler's laws of planetary motion. Now we can't start this video without talking about a bit of history. Now the time period when these laws were inferred just makes them even more amazing. No telescopes for Johannes Kepler, so he had to use raw data from Tycho Brahe, a Swedish mathematician who just uses observations really. The laws that we're going to be investigating today describe quite brilliantly planetary motion, and to be inferred by someone that didn't even have a telescope makes it even more incredible. Kepler's first law states that all planets move in elliptical orbits with the sun at one focus. Now, we now know that not only planets orbit things, so we can generalize this by just saying all orbits are ellipses with the center of mass of the system being at one of the foci. You can see this illustrated on my terribly inaccurate diagram. In this case, the sun is at one of the focuses of the ellipse, and the other focus is marked in purple, and the Earth is going around it in its elliptical orbit. I must add that the Earth's orbit is nowhere near this elliptical. And of course, this diagram is not to scale. Just while we're on the topic of orbits and their shapes, it's very important that we talk quickly about periapsis, apoapsis and semi-major axes. As you can see on an orbit, there are 2 points, one closest and one furthest from what it's orbiting. These are called the apses, with the closest being the periapsis and the furthest being the apoapsis. The distance between the periapsis and the centre of mass of the system is called the minor axis, and the distance between the centre of mass of the system and the apoapsis is called the major axis, seen here marked as X and Y. When people tell you that the Earth orbits the Sun at a distance of 1 AU, 1 astronomical unit, this is not the minor axis or the major axis. It's called the semi-major axis and is just an easy mathematical average of the minor and major axes. Denoted by the letter A, you can just work this out by adding the major and the minor axis and dividing it by 2. Now we've got Kepler's first law sorted, we can move on to his second law. This law states that a line that connects the object to the centre of mass of the system that it's orbiting sweeps out equal areas in equal amount of times. Now this one's a bit harder to think of, so I'm going to draw a quick diagram. Let's take a time t and see how the planet behaves. Now, in both cases, the planet has moved a certain distance. Now if you draw a line from where the planet was to the star, and where the planet now is to the star in both cases, and then fill in the area, the two areas are equal according to Kepler. Now what does this show us? Because the planet closer is moving a much smaller distance, and hence the area should be much smaller, it must be travelling much faster. Since then we've discovered gravity. We know that as you get further away you gain gravitational potential energy, therefore you lose kinetic energy, therefore you must be going slower. But back then they had no idea about this, so the fact that it could be inferred was very cool. Now we've sorted the second law, we can move on to his third law. This law states that the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. In plain English, this just means that the time it takes to go round squared is proportional to the semi-major axis cubed. Now t squared doesn't equal a cubed, there's a constant of proportionality involved. In the background you can see me deriving this constant of proportionality. Now if you want a video showing you exactly how to do this, just leave a comment below. Kepler must have gone through masses of data to find this, because it's just crazy. But we've all got to say a big thanks to him for that. And that's it, now you're familiar with Kepler's 3 laws of planetary motion. If you enjoyed the video, please leave a thumbs up and subscribe if you really enjoyed it, because more content like this is coming up. And once again, thanks for watching.